Okay, so in this part, we will go back to logistic regression and we will try to come up with the weight update equation for both the weight and bias. And we will also see how we can derive the equations for a two-layer neural network. Last time we saw the main structure of a two-layer neural network when we had many nodes like disconnected to other nodes, but we didn't really know how to get the weight updates for each one of them. So right now we will start with deriving this for just one node of logistic regression, okay? Because it's very directly related to the same proof of doing this to two-layer neural network or even a deep neural network with a lot of layers. Okay, so now we are looking again at logistic regression. And we basically have three things. We have X, our features, we have weights, and we have our bias. And all of that is going into the calculation of the net input. So we have Z equals W transpose X plus bias, and then we go ahead and calculate our activation 5Z, which is the sigmoid activation. Okay. And for simplicity, let's call activation, let's call 5Z, we would call it A. Okay. A for activation. So just to make it easier. And then we'd have our Y hat, our predicted value. And at the end, we are comparing this to Y and asking whether this would equal the true label. Okay. So all of this was actually summarized as a node, just taking the value of X. Okay. And it would give you an output of Y hat. Okay. So this is one node. So now we would see how we can get the weight updates, and then we would use the same concept for the two-layer neural network. So first of all, we are following something that is called the chain rule when we are getting the derivatives. So let's say that you are getting a derivative of something in brackets. You will take the derivative of the whole bracket and you will multiply this by the derivative of what is inside the bracket, okay? And that is the main thing that we do when we have a function within a function, okay? So here we have a problem that we cannot really get our cost value and calculate our cost up until this point. So we cannot just update the value of W at this point because we have to calculate the cost, the difference between Y hat and Y. Okay. And after doing that, we can only calculate the derivative of this cost. Okay. Okay. So just remember that in gradient descent, we wanted the derivative of the cost with respect to W. Okay. Which was delta W. And we were updating our cost with this weight update value. And we're doing the same thing for the bias. Okay. With delta B. So our main objective to update the weight is to get the derivative of the cost with respect to W. Okay. But here we have middle functions, meaning that this is not the final function because we are projecting the value of Z on the logistic, on the sigmoid function. Okay. So we have a function and then another function after projecting this on the sigmoid. And then we calculated the cost. So according to the chain rule, we would have to get the derivative of the cost at the end of this comparison with respect to this first, with respect to this function first, to A, okay? And then we need to get the derivative of that function with respect to this function, to Z, okay? And then we go to the weight. So it will be the derivative of Z of this function with respect to the weight. Okay, so when we multiply all of them, like so, we would have our delta, our derivative of the cost with respect to W. So our derivative will basically equal to this multiplied by this multiplied by this. Some people actually prefer to look at this in this way, okay? But this is not very accurate. It's just intuitive. Like imagining that I'm gonna remove this, okay? And I'm gonna, because that's like so, so this will eliminate this, and then we would end up with um, the derivative of the cost with respect to W, okay? Okay, so any questions on this? Any
No,
question?
no questions.
Okay, so let's look at this with the equations. So for the cost, for calculating the cost, we have the equation for L, the cost, which is in the logistic regression. So it's a cross entropy. So it will be like that, 1 minus y, log 1 minus y. This is y hat, okay? Okay, so this is the cost. So right now, let's remember our main objective is to calculate the derivative of the cost with respect to W, which equals the multiplication of all of these derivatives. So let's start at the beginning, like calculating this first derivative. Okay, so right now we need to have this derivative of the cost with respect to A. Okay. Okay, let's just think about it. Okay. Let's just think about it. I just put the hat in incorrect place. That should be y hat. Okay. So y hat is the result of the activation, the result from the activation. So it's actually A. So we can just say that this y hat is A. Okay. So right now we need to take the derivative of this with respect to A, because that's the cost function. So I'm taking the derivative of it with respect to A. Okay, so the derivative of the log is basically you put what is after the log, you put it here, okay, in the denominator, okay, and uh, then it will be multiplied by the derivative of that, the derivative of A, which is 1, okay, multiplied by minus y, okay, plus the same thing here. So 1 minus A, denominator, okay, and then above it will be minus 1, okay, it will be minus 1, okay, that's why this is turning into plus, and then 1 minus y. Okay, so is this derivative clear?
Yeah.
Okay, good. So this is our first derivative, which is important, and that's why I'm keeping it like that. And then let's look at the second derivative. So the second derivative is the derivative of the activation function with respect to z. Okay, so that's a little bit tricky because activation, derivative of activation with respect to z. So let's see how to calculate this. So our activation is sigmoid. So 1 over 1 plus e to the power of minus z. That's our activation. So we need to get the derivative of this with respect to z. Okay. So this would be, so the derivative of this multiplied by this. Okay. So this would give us 0. Okay, because the derivative of 1 is 0 multiplied by this, it will give us 0 minus the derivative of that multiplied by 1. So the derivative of this part with respect to z, e to the power, let's say 2x, the derivative of e to the power of 2x with respect to x, it would be e to the power of 2x. So it will be as is. It will come as is, okay? And then multiply it by the derivative of that, which is 2. So it would be 2 multiplied by e to the power of 2x, okay? Let's apply the same thing here. So it will be e to the power of minus z multiplied by the derivative of that. Derivative of minus z with respect to z, it will be minus 1, okay? Minus 1. But here, let's remember, we took the derivative of that multiplied by this minus the derivative of this multiplied by that. So there is minus between them. So this will be positive, okay? And then we will square this denominator. Okay, so it's a normal derivative. I'm just trying to remind you with the derivatives, okay? So what we can do next is basically we can just do a workaround. So we can add 1 and then subtract 1 as if we're not doing anything. So it will be 1 minus 1 plus e to the power of minus z over 1 plus e to the power of minus z squared. Okay, and then we will be taking these two, e to the power of minus z plus 1. So it will be 1 plus e to the power of minus z over this quantity. Okay, minus 1 over this, minus 1 over this. Okay, so this will just remove the square, and then we will end up with 1 over 1 plus e to the power of minus z, okay, minus 1 over 1 plus e to the power of minus z squared. Now let's take 1 over 1 plus e to the power of minus z. Let's take it as a common, okay? So this will be common. So it will be multiplied by 1 minus 1 over 1 plus e to the power minus z. Okay, so let's look at this. So what is this part? This is the activation, right? This is the sigmoid function. And this is also the sigmoid function. So that's why I was just trying to simplify all of this. Because now we can write all of that in a very compact form. A multiplied by 1 minus A, right? A multiplied by 1 minus A. So any questions on this?
No.
Okay, so this is our second derivative, this derivative, okay? Now let's move to our third derivative. And then I will just take all of them and multiply them together. So that's 1 and that's 2. And let's look at the final derivative, which is actually very easy to get. So it's the derivative of z with respect to w. Derivative of this function with respect to w. So it will be x. Okay. Okay, perfect. And this is our third derivative. Okay, we just need to multiply them. Okay, so let's multiply 1 by 2, and then we'll see how to multiply it by 3. Okay, just multiplication by 3 will be easy because it's just multiplication by x. Okay, so let's look at this. This function minus y over a. Mhm. Okay. Okay, so this function, let's multiply it by this. A 1 minus a. Okay, let's do this multiplication. So basically, when we take this multiplied by this part, a will remove a. Okay, so we would have minus y multiplied by 1 minus a. And when we multiply this by this part, 1 minus a will remove this 1 minus a. Then we would have a multiplied by this, so it will be a minus ay. Okay, and then we can multiply this inside, so it will be like that, plus ya plus a plus ay or ya, doesn't matter. Okay, sorry, this is negative. Okay, and then we can simply remove this with this, then we will have a minus y. So this is the multiplication of the first derivative with the second derivative. You see, things are getting more simple, right? Getting really simpler. Okay, so that's the multiplication of them. Okay, so let's look at this because this is really nice because we can just multiply this, by x, and then we will be getting our weight update. So basically our weight update will be multiplying this a minus y, we multiply it by x. Okay, I think this is really nice because if you think what is a? A is just y hat. So this is actually y hat minus y multiplied by x. Okay, and we just wanted to tune this down a little bit to smooth the effect with the learning rate. And this was exactly the weight update function that we were using, right?
Yeah.
Okay, so how about the bias? I think it's very simple because for the bias, you will be using the same functions. You will just be getting the derivative of z with respect to the bias. So the derivative of z with respect to the bias will be 1. Okay, and that's why we were not multiplying by x, we were just multiplying by 1. So we'll see y hat minus y. Okay, and that was our equation for the updates. So any questions on this part?
Yeah.
Okay, good. So right now, let's keep in mind that this equation and this equation, because we will really need them when we are driving this for 2 layers. Okay. So let's look at our neural network again and see how we could perform the weight update for it. Okay. So let's say that we have 3 features. And let's say that this is our first layer. Okay. So this is our first hidden layer. Both of them are hidden because that's the input. Okay. And the result here is the output y hat. That's the output layer. And every node is taking all the features. All features. Every classifier is taking all the features. Okay. And we say that this is a dense network because it's fully connected. Each node is connected to all other nodes. Okay, so right now we can say that this is hidden layer 1, and this is hidden layer 2. Okay, I think this is good. So right now we can put some variables inside. So basically our features are multiplied by the weights. So instead of just considering weight and bias, I would just consider all of them to be weights, just for simplicity. So we have weights multiplied by the features. Okay. And for every connection, we have a weight. We have a different weight. Okay. And of course, for every feature. Okay. And inside of the node, because this is a classifier, I will just put 2 numbers. So one of them to represent the number of the node, which is here, 1. Okay, node 1. And the other number to represent the layer number. Okay, so this is for layer, and this is for node. Okay, that's good. So this one will be second node, layer 1, and this will be third node, layer 1, and this one will be node 1 of layer 2. Okay, so it's very important to think about this because what is happening inside of this node that we are treating everything before this point as a feature. We are treating all of those as a feature. It's very similar to the behavior of the second layer because the second layer doesn't really care about what was happening before it. It will just treat all the values before this layer. It will also treat them as features. So actually now the features of layer 2, the features of layer 2 are the values after the activation of layer 1. Okay, so we'll just take those values as the features of layer 2, multiply them by U weights. So any question in this kind of intuition? Okay, so when we have more than one hidden layer, we say that this is a deep learning model. So deep learning is nothing more than that. It's just stacking more than one layer, more than one hidden layer. Okay. And the nice thing is that when you have a network like this, if you were just initializing all the weights with zeros or the same random value, this wouldn't be good because all of your classifiers will be trained from the same place. Basically, if all of the classifiers have the same weight value, they will be going to the same minima. They will be going to the same place, trained similarly. So you wouldn't be gaining any new information by adding more nodes. That's why we are initializing the weights randomly, because when you initialize the weights randomly, some of them will be here, so they will be learning interesting features there, and some other weights will be here, going to different places. Okay, so it's very nice to have your weight initialization with random values. There are some other algorithms for weight initialization, but for the sake of this, we are using random values. Okay, so each one of those is, of course, a vector. So W transpose will be a vector. Okay, and W transpose for of course, this is one weight. So this is the vector of W transpose, not for this weight. Okay. So this at this activation, we are getting all the weights, putting them in a vector, W transpose, and then multiplying them by X values to calculate Z. And then we calculate 5Z or A by doing like a sigmoid or any other activation function. So we can basically think that we have this row and we have another row here for the weights for this second node, taking all the features like so and calculating its weight, okay? And another vector here. So for the sake of calculations, and instead of doing this as we were doing before, like taking W transpose X, like that, when we do dot product, it's just flipping this and multiplying this with all the data. And instead of doing that, we stack these vectors in a matrix. So this would be the vector of the first node. This would be for the first node. And then we put the second node underneath and so on, such that when we do the dot product, it will still multiply this matrix by this matrix and give us the values, the Z values for different nodes at the same time, and instead of doing this in a loop. Okay, so it will be much easier like that. So any questions on that?
Yeah.
Okay, good. So let's see how to do this derivation of weight updates, but for the two-layer network. Okay. So we have three inputs in the beginning. And right now I will put the number of layer. Okay. So I will put W1, meaning that that's the input going to layer one. Okay. So we have W1, weight one, And this bias is for the first layer. And then we'll have Z1. That's the Z going here in the first layer equals W1. Of course, it's transpose, but I will just, for simplicity, just say W, X plus B, B1. And that's the activation of the first layer. Here I will be representing the sigmoid function with sigma, just for simplicity, and instead of writing the whole equation. So this would be the activation of Z1. Okay. And then this is connected to layer 2. Okay. This is connected to layer 2 here. Okay. So we'll be calculating Z2. It will be W of 2, the weight of the second layer, multiplied by the feature. So what would be the feature of that layer? So it would be W2 multiplied by what? What do you think? So it would be W2 multiplied by the feature of that. So it would be A1. Okay. So it would be W2 multiplied by the feature. As we said, this node is considering the previous one to be the feature. Okay. So that's why we're writing in A1 plus B2, the bias of the second layer. Okay, so here we can put our parameters W2 and B2, okay, because we also need to calculate them. We also need to calculate them. So we can put here W2 and B2 because we would really need to calculate them. So when we get to the coast, we need to trace this back to go in a back propagation. All we were saying here is called the back propagation. We're propagating backwards to calculate the weight update. Okay, so we need to propagate backwards and calculate the weight updates and bias updates for layer 2 and then for layer 1. This would be A2, the activation, would be the sigmoid applied to Z2. And then we have our Gusta function, taking this activation, the output, and comparing this to the through label. Okay, and this is of course asking whether y hat equals y. Okay, so I think now we are ready to look at the back propagation because here we will get the derivative of the ghost with respect to A2. Okay. And then here we will have the derivative of A2 with respect to Z2. Derivative of Z2 with respect to A1. Derivative of A1 with respect to Z1. And eventually we would have the derivative of Z1 with respect to W1. And for the chain rule, we just need to multiply all of these together. Okay, so any problem in that so far?
No.
Okay, so let's recall the derivative of the cost with respect to the activation is actually similar to what we get for the logistic regression because that's the derivative of the cost with respect to A, right? So it would be this quantity, okay? It will be 1, okay? So instead of writing down the equation, I will just say 1, okay? Here. Okay, so right now you can really see how deriving this for logistic regression is making things very easy. Okay, so the derivative of A2 with respect to Z2, okay? Also, derivative of A with respect to Z, okay? The only difference is that we put A2 and Z2 instead of A and Z, but the derivative itself is the same. It wouldn't really make any difference. So the derivative is like that, okay? And instead of saying A, it will be A2, okay? So here I will just put 2. Okay, so what is the multiplication of 1 and 2? So let's get this part first, okay? Multiplication of 1 and 2, multiplication of 1 and 2 were in this slide when we multiplied them, it was a minus y, a minus y, okay? So let's put this. So the multiplication of this will be a minus y, but the difference here is that we are at the second layer, so it will be a2. So a2 minus y, okay? So this would be this derivative. Okay, good. So right now we are at this point, and there is something important. We also need to get the weight update at this second layer and the bias update at this second layer. So we need to get the derivative of Z2, okay, with respect to W2 and the derivative of Z2 with respect to bias 2. Okay, so we get this, and we will be multiplying this according to the chain rule by this in order to get the weight update, okay, for the second layer. So basically, instead of saying that this is the derivative of the goose with respect to z, okay, we can name this dz, okay? So because this is the second layer, we can say that this is dz2, okay? Or just ignore all of that, ignore that, just not to have any confusions, okay? Okay, so we have this quantity here, and we now need to multiply it by the derivative of that. So it's the derivative of z with respect to w2. So the derivative of z2 with respect to w2. So this would give us a1. A1. Okay. So if we take this, multiply it by a1, okay, just let's name it dz2. Okay. So if I take dz2, multiplied by A1, I will be getting the weight update that I want of the second layer. Okay, I really need you to listen to this recording of the lecture, okay, and try to do this yourself by hand, okay, because it's not very difficult. It's just a lot of operations, but we are just like repeating the whole thing over and over again, okay. Um, so now we need to take the derivative of Z2 with respect to B2. So this will be 1. So it will be dz2. Okay, so right now we know this quantity, we know this, and we know this. We can calculate the weight update at these ports, okay, of the second layer. So how about the first layer? How about the first layer? So right now we need to take the derivative of Z2 with respect to A1, with respect to A1. So it will be W2. Okay, so because we named this dz2, we can just use it here. So we can say that this will equal dz2. Again, the derivative with respect to a1, it will be w2 divided by w2. Okay, so that's the derivative at this port. And then let's get the derivative. Let's call it dA1. dA1, like relative to this name. okay, and get this derivative, which is the derivative of the activation with respect to Z1. So that's the derivative of the activation. So the derivative of the sigmoid. So I would just name it sigma prime. Okay. And we can just take it from the logistic when we get this derivative of the sigmoid. Okay. I'm just putting this here instead of writing more equations. So this would be the derivative of the sigmoid, of course, multiplied by this quantity according to the chain rule. So it would be W2 dz2. Okay. And then we can name this dz1 according to this name. Okay. Now you can take dz1 multiplied by the derivative of z1 with respect to the weight to get the final update. Okay. So what is the derivative of z1 with respect to w1? What do you think?
Mm.
The derivative of z1 with respect to w1. It will be x, right? So it will be basically taking dz1, taking this whole quantity, dz1, multiplying it by x. Then you will be having dw1, which is the weight update of the first layer. Okay. Similarly, we would have db1, which is dz1 multiplied by 1, because the derivative of that with respect to bias is just 1, multiplied by 1. Okay. That's nice because right now we got the two layers, the weights and biases of the two layers. This is for the first layer, and the one here, the one here for the second layer. Okay. And this happened when we back propagated this to get the weights here and then up until this part. So any questions on this?
No.
Okay, good. So just one thing, that if we have a network with a lot of layers, if we have a network with a lot of layers, so let's say we have a third layer here, or like 6, 7 layers, and we train our network, then the network will have the optimal weights at every layer. Then we can simply cut our network, okay, and just take the values of those nodes, okay, with the weights and everything as our features. Because if you notice, every node is treating the previous one as a feature. So we could simply say, and instead of using the features as is from the beginning, we could train a very deep neural network and then use this trained network activations as new features. And this is called the transfer learning, because you are transferring the information learned from training the classifier model in the beginning to extract the new features from your new problem. Okay.